Gomez. I am now at UNAM Morelia in Mexico. I will talk about galactic angular momentum in the TNG simulation. I've been doing this work along with Shai Genel and Laura Salins. In fact, this work is pretty much complementary to what Shai just discussed. So, okay, so I will. This is work in prep about galactic angular momentum in TNG. I'll discuss some results, and then if there is time, I will also like to briefly discuss this finished project about optical morphologies and synthetic images. So, okay, so the specific angular momentum of a galaxy is one of its main properties. In fact, it might be the second most important property of a galaxy after its stellar mass, in my opinion. And you might have seen this relationship between J star and M star. Well, in fact, Shai showed it 20 minutes ago. So some people know it as the fold relation. I just know it as the J star M star relationship. And yeah, it shows that galaxies follow a trend, a power law with a slope of 2/3 in this diagram. And also there is a split by morphology, so that disks are above the spheroids in this relationship. So on the left, this is a sort of like a cartoon model in which the lines are perfectly parallel to each other. These are observations from before 2012. In reality, the lines might not be parallel, but it's still a useful model. So, so this relationship has been explored in a number of simulations. Illustris is one of them. And yeah, so the preliminary work with Illustris showed that we were on the right path to reproducing the correct angular momentum of galaxies. Here, the dashed blue and red lines are essentially the observations from the previous plot. These lines, and the black is the overall Illustris relationship. And the other two lines are what you get if you separate galaxies by different properties, which are shown in the bottom panels. So there was rough agreement. Although if you notice very closely, the trend in the simulation is somewhat shallower than in the reality. So now there is a new simulation, as you know, IllustrisTNG, and what we get is actually closer than the observations than in the original Illustris. So here again, the dashed blue and red lines are the observed trends, and all of the other lines are what we get in the simulation. The different colors correspond to different morphologies, which we quantify using this kappa parameter, which essentially measures the fraction of kinetic energy invested in ordered rotation. So it's what I call a kinematic morphology. And yeah, so in IllustrisTNG, actually the agreement is quite striking in my opinion. And you get the most disky galaxies are almost on top of the observed trend, and the most spheroidal galaxies are also in very good agreement with observations. Of course, some people might argue that this kappa parameter is meaningless for observers, and it's so this is why we explore a different morphology measurement. Here again, we have a kappa on the left, and on the right, here I'm using the morphological classifications done by Mark Huerta's company on TNG galaxies, which are trained on SDSS. So actually, Mark will talk more about that on Friday. So you should definitely stay until then. So yeah, in both cases, there is agreement with observations. In this here, the data points are more up to date. So these are the most recent measurements from Fall and Romanowski in 2018. Yeah, and I should also point out that this is a very inclusive sample of galaxies. So I'm basically including all galaxies, not just the the tails of the spheroids and disks. So a very closely related quantity, which I also mentioned, is the retention factor. So this is the the fraction of the halo's specific angular momentum that is retained by the galaxy itself. So Shai mentioned that traditionally this factor is believed to be around 80% for disks and around 10% for spheroids. Here, at least using this using this definition, we get around 50% for disks, 20% for spheroids. Although this would change if we change the ranges here. And we get something very similar with the Mark's deep learning classifications, except maybe at the high mass end where disks have lower retention factors. Although if you think about it, there shouldn't be disks at this mass range. So so the model is not perfect yet, right? But there is agreement. So you might also wonder what's the redshift evolution of this J star M star relationship, and we find that the relation became shallower. It's shallower at earlier times, as is shown here, and it's also shallower if you consider the inner angular momentum. So, for example, within one effective radius, which is what I show on the right hand here. So if you consider the total angular momentum, so this is measured out to for the entire galaxy, you get a scaling of around a logarithmic slope of 0.6. And if you do it for the inner angular momentum, you get a logarithmic slope of 0.3 roughly. And I'm showing this. This is important because this is roughly what observers can measure with like IFU, very very large IFU programs, without doing some kind of fancy extrapolation, taking into morphology into account, etc. So you can also notice that at the high mass end, the total angular momentum shows stronger redshift evolution than the inner angular momentum. This is shown more clearly here. Here we have a redshift on the x-axis and a specific angular momentum. And each panel shows different masses. So the least massive galaxies, in the least massive galaxies, the inner and the total specific angular momenta evolve very similarly. But this changes for the most massive galaxies where the inner angular momentum seems to plateau at some point, while the total angular momentum keeps growing. So, so you might wonder, is this evidence of inside-out growth, or do mergers have something to do with it? So I will come back to this in a few slides. So things start to get really interesting when you compare the stellar angular momentum to other galaxy properties. So here again, we have the J star and star diagram. I'm separating galaxies by different galaxy properties in each panel. On the left, we have the stellar age of the galaxy. So of course, it shows that younger galaxies have higher angular momentum at a fixed mass. Then this is the spin of the host halo. And of course, galaxies that live in faster spinning halos have more angular momentum. So this is intuitive, right? What we were not expecting, and which actually we didn't find in the original Illustris, was this relationship with the black hole mass of the galaxy. So that galaxies with more massive black holes have less angular momentum, and galaxies with less massive black holes have higher angular momentum. So that's interesting. And so on closer inspection, we decided that, well, we found that this trend right here with stellar age is mostly set by the black hole mass. So this is what's driving things here. And the halo spin parameter is also like an independent factor. So we explore this in more detail in this plot, which might be a lot to digest. But on the y-axis, we have the black hole mass relative to the stellar mass. On the x-axis, we have the spin of the halo. And the colors represent the J star, right? The specific angular momentum. I normalize it so that it's roughly the same range in every panel. And these are the less massive galaxies, the least massive galaxies. Then mass increases, along the rows, and these are the most massive galaxies. So usually, when I make this kind of plot, the direction of the color gradient tells you how. What are the dependencies, which factor is more important. And here we find that both factors, both the black hole mass and the halo spin, seem to be, in some sense, equally important because the color gradients are diagonal, right? So, and another cool thing about this plot is that the black hole mass and halo spin themselves are correlated, as you can see with the contours, right? So galaxies in on the left side, galaxies with that formed in slowly rotating halos have more massive black holes and vice versa. So we're still disentangling what's going on, but it seems that there are, a galaxy acquires its angular momentum from at least two reasons. One is, like the angular momentum it inherits from its parent halo, but also part of it is that if a galaxy is in a fast rotating halo, then it's harder for gas to be accreted to the center. And then the black hole would have less energetic feedback, and so on. So the black hole acts as an amplifier for the effects on the angular momentum. So a quantity that is very strong, very closely related to the galactic angular momentum is the size of the galaxy, and according to analytical arguments, galaxies that formed in faster rotating halos should have larger disks, right? This is a simple analytical argument, and this is what we find here. So this is the half mass radius of a galaxy as function of stellar mass, and at least in this mass range, we find that the ones that formed in fast rotating halos have larger disk sizes, right, than the spheroids. So that's nice. However, the trend disappears at the massive end. So it's interesting to place this plot next to the ex-situ stellar mass fraction. So the fraction of stellar mass that is accreted from mergers as a function of stellar mass. And as you can see, galaxies become ex-situ dominated or merger dominated at around this mass, and which is also the mass where you lose this nice relationship between sizes and halo spin, right? So so this suggests that mergers have something to do with this. So the next thing I did was to repeat this plot of J star and star, but in this case, each panel is splitting galaxies by different merger statistics. On the left, I have the ex-situ stellar mass fraction, and then I have the mean merger loopback time. So this is like a weighted average of the times of all the mergers that a galaxy has ever had, and this is the mean, also the average of the average gas fraction of all the mergers that the galaxy had. So there's basically no relationship here, right? There's nothing. So mergers, the angular momentum of a galaxy doesn't care about mergers on average. But when you repeat this on for the profile, the cumulative distribution of angular momentum, then you actually see that that mergers have a clear effect. So that galaxies that have more mergers or more accreted material or more dry mergers tend to have a more extended spatial distribution for the angular momentum. Yeah. What else? And okay, I will quickly go through this other project about optical morphologies. So essentially, we made synthetic images for the Pan-STARRS survey, for the POGS survey, which is part of Pan-STARRS. We made the synthetic images using the SCIRT code, which I think the main reason I use SCIRT is that it has this nice feature that it can do the radiated transfer directly on the Voronoi mesh, which is perfect for simulations run with a repo, right? Which also solves the hydrodynamics on the Voronoi mesh. This is an example of one of the mock images that we made. On the left, this is what it would look like without any dust attenuation taken into account, and this is what comes out of SCIRT with the dust attenuation and scattering and all of those effects. So as you can see, there is a difference, right? There is a dust lane here, as you can see. Here's another example. Here's another example. And then you can analyze these images in exactly the same way as you would analyze a real image. So here we're measuring the various morphological parameters using this StatMorph code, which I developed during my postdoc. So it's actually public, so you can measure non-parametric morphologies like Gini, M20. You can also do single component Sersic fits, etc. So we made a very apples-to-apples comparison between observations and theory. This is what we get for the Gini M20 diagram. I don't have time to explain what this is, but some of you know what this is. So this is pan stars on the left, the observations, and there's IllustrisTNG, and this is the original Illustris. So what this means is that in the original Illustris, galaxies were too disky, and IllustrisTNG is better. We measure many other morphological parameters. So each of these is a different morphological parameter as a function of stellar mass. So black is the observations from pan stars, blue is IllustrisTNG, and red is the original Illustris. So in every single parameter that we measured, the new IllustrisTNG is within 1 sigma of the observations, which was not the case with the original Illustris. Here are other parameters, like here's the Thoracic Index, for example. So IllustrisTNG was a huge improvement in morphology with respect to the original Illustris. And again, Mark Huerta's company will talk more about this in his talk on Friday, using deep learning classifications. How much time do I have? Okay, I'll just jump to my conclusions. So, very quickly, yeah. So I have a PhD student who is working on he's also working with TNG, and he will continue this line of work of making synthetic observations. But this will be more geared towards IFU observations, for example, from Manga and Khalifa. This is extremely preliminary, but he might have some actual results soon. And yeah, I'll leave you with my conclusions. So the recent, IllustrisTNG produces galaxies with very realistic angular momentum properties, and we find that it correlates with stellar age, halo spin, black hole mass. On the other hand, mergers do not have a net effect on the angular momentum on average, but they do have an effect in pushing this angular momentum outwards to larger radii. And then this other project, which is actually finished and published, is just we made synthetic images of TNG using Skirt, as realistically as we could, and we compared to pan stars. Yeah, and this places some constraints on the TNG model, and we also made the code public. So, yeah, thank you. Any questions? Yeah.
Thank you very much. We have time for questions. Yes.
Yep. Hi. Yeah. Hi.
So I found interesting that in the plot where you have the stellar specific angular momentum as a function of stellar mass colored by halo spin.
Yep.
Yeah, way back.
This one?
No. Oh yeah, yes, that's right.
Okay.
The central one.
Right.
So you have stellar mass range also 11 to 12, and which is something that you had seen before in your 2016 paper, looking at the halo spin parameter. You
Right.
see a correlation between the high rotation and dispersion.
Right.
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 So you see one here.
Right.
So I'm wondering, is that because you're using here the IllustrisTNG, or why is that?
No, that's a very good question. Yeah. So the answer is it's a bit subtle, which is that the angular momentum, the specific angular momentum, is not the same as kappa, right? So in that paper, I mostly used kappa, which is the fraction of kinetic energy invested in ordered motion. So I actually have an appendix in that paper about the differences between kappa and the angular momentum, because angular momentum is it's a different quantity. It's somehow weighted by distance, right? So it doesn't behave exactly in the same way. For example, you can have an elliptical galaxy with kappa, very low value of kappa, spheroid, with high angular momentum. That can happen. So essentially, the correlation between angular momentum and kappa essentially disappears at the high mass end, which is why I do find a trend here that I did not find with kappa with the original Illustris, right? Yeah.
Okay, another question. Here.
I have not done bulge disk decompositions, right? It's because they are not so easy. So you're saying that the bulge mass could be more fundamental than the black hole mass or something like that? No.
Observation, I don't know what things like now, but for a while there's been a discussion of does bulge mass correlate more strongly with black hole mass, or stellar mass correlates with black hole mass, which would, if that's true, that goes along with what you're finding here, I think, with the spin correlating, anti-correlating with black hole mass.
Okay, yeah, that's very interesting. I think we should talk more, but the short answer is that I have not looked at bulge masses very much. Yeah.
So maybe we can take a last question while the next speaker sets up. Any other questions? Frank?
Does IllustrisTNG produce any of the real slow rotators? Basically, approaching the zeroing line, the massive end. Do you see any of those? And they're also round.
Yeah, so I have not made, like a, the fast and slow rotators are based on this MCLM definition.